Hello and welcome. Professor Philip here, and I'm back in my office. I want to talk to you a little bit today about discrete probability distributions. It's chapter 5, and you're going to have to do a few problems from that chapter as well. More specifically, I wanted to talk to you about binomial probability functions. The binomial probability function is the probability of x successes in n trials. That's what f sub x is here, with the probability of a particular sequence of trial outcomes with x successes in n trials represented by p sub x 1 minus p raised to the n minus x, where n over x in the parentheses, as you see here, is n factorial over x factorial multiplied by n minus x factorial. And I wonder if you're thinking, what is a factorial? And fairly simple. It's just n to the exclamation point, which equals in algebraic terms as n times n minus 1 times n minus 2 times n minus 3 and so on. So for example, 4 factorial, represented as 4 to the exclamation point, is 4 times 3 times 2 times 1, which equals 24. 5 would be 5 times 4 times 3 times 2 times 1, or 3 factorial would be 3 times 2 times 1. And oh, don't forget, 0 factorial, that all equals 1. So the number of trials over the number of successes is represented by n factorial, the number of trials, divided by x factorial, the number of successes, times the number of trials minus the number of successes, multiplied by the probability of a particular sequence of trial outcomes, which is p to the x, 1 minus p, n to the x. Sounds confusing, but work through it, work with these problems, and you'll find that they aren't really too difficult to do. There's just a lot of multiplying and dividing. So let's do a problem, and then we'll also work through some other ways to do this type of binomial probability function. So start off, let's consider 3 students enter the class. The teacher estimates the probability that any one of these students is going to get an A is 0.3 or 30%. And what we want to know is what's the probability that exactly 2 of the next 3 students will pass. So the first thing we have to do is figure out what we know. The success is an A, failure is everything else. N equals the number of trials, which is 3 students. P is the probability, 0.3, that's given. And the number of successes we're interested in is exactly 2. And everything else is considered independent. So let's walk through these numbers. Again, n given x amount of times the probability of a particular sequence of trial outcomes, p to the x, 1 minus p, n raised to the x, with x successes and n trials. So what we have here is a number of different trials and successes. In the first line, we have 0 successes under 3 trials, which is 3 factorial over 0 factorial, 3 minus 0 factorial, which is 3 factorial over 3 factorial, goes to 1, times 0.3 to x, which is 0, and 0.7, 1 minus 0.3, to n minus x, which is 3 minus 0, which is 3, and we get a total of 3.43. Our probability, therefore, that we will have 0 successes on 3 trials is 34%. Now, if we run through the math again, for 1 success on 3 trials, which is 3 factorial over 1 factorial times 3 minus 2, which is 1 factorial times 2 factorial, times 0.3 times x is 1 now, and 0.7 to 3 minus 1 is 2. So our probability that we will have 1 success or 1A given 3 students is 0.441. Here we have 0 students getting an A, and that's 0.34. 1 student getting an A would be 0.441. Now, the point of interest. We have 2 students success, which is an A, out of 3 trials. 3 factorial divided by 2 factorial, 3 minus 1 factorial, which is 1 factorial. 0.3 to the 2 raised to the 2, 0.7 raised to the 1. So we have a 0.189 or 18.9% probability that 2 successes out of 3 trials, or 2 students will get an A out of the next 3. We also would like to know what happens, since we're filling all this out, if 3 students out of all 3 students get success or an A. 3 factorial over 3 factorial, 3 minus 3 is 0 factorial, but remember, 0 factorial, as in the first line, is 1. 0.3 times 3 and 0.7 to the 0 equals 0.27 probability that all 3 students will get an A. Now, there's another way we can go about doing this. We can do the mathematics through the function, which isn't too difficult as long as there's not too many successes and too many trials. But we can also go to the book, and so there's in the back in the appendix, there's a probability function, or I should say a table of binomial distribution. And you can go to that table, and we have the probabilities here. Now, our probability of success, 0.3, our n, which is our number of trials, is 3. And here is the successes, 0, 1, 2, 3. Remember 0, we had a 0.343 from our mathematics. For 1, we had a 0.441. And for 2 successes, x successes, which we were trying to find, 0.1890, just like the math showed. So you can always just come to the tables if you know what the probability is, you know how many trials you have, and you know what the success is, and it's already calculated for you, and you don't need to go to this probability function. Both ways work. Both ways are fine. You have to find the one that works best for you. Again, the probability tables are a little bit quicker than going through the mathematics, and you don't have to worry about dropping a term or such. So anyway, I wanted to walk through one of the problems that you'll have to do. You're more than welcome to always use the probability tables when you're doing binomial functions or binomial probability functions. Just you have to find which one is best for you. With that, I'm Professor Philippi. If you have any questions, send me an email through Canvas email, and I'll get right back to you. Have a wonderful, wonderful week.